Transformers are taking the natural language processing world by storm. These incredible models are breaking multiple NLP records and pushing the state of the art. They are used in many applications like machine language translation, conversational chatbots, and even to power better search engines. Transformers are the rage in deep learning nowadays, but how do they work? Why have they outperformed the previous king of sequence problems like recurrent neural networks, GRUs, and LSTMs? You've probably heard of different famous transformer models like BERT, GPT, and GPT-2. In this video, we'll focus on the one paper that started it all. Attention is all you need. To understand transformers, we first must understand the attention mechanism. To get an intuitive understanding of the attention mechanism, let's start with a fun text generation model that's capable of writing its own sci-fi novel. We'll need to prime the model with an arbitrary input, and a model will generate the rest. Okay, let's make the story interesting. As aliens entered our planet and began to colonize Earth, a certain group of extraterrestrials began to manipulate our society through their influence of a certain number of the elite of the country to keep an iron grip over the populace. By the way, I didn't just make this up. This was actually generated by OpenAI's GPT-2 transformer model. Shout out to Hugging Face for an awesome interface to play with. I'll provide a link in the description. Okay, so the model is a little dark, but what's interesting is how it works. As the model generates text word by word, it has the ability to reference or attend to words that is relevant to the generated word. How the model knows which word to attend to is all learned while training with backpropagation. RNNs are also capable of looking at previous inputs too, but the power of the attention mechanism is that it doesn't suffer from short-term memory. RNNs have a shorter window to reference from, so when the story gets longer, RNNs can't access word generated earlier in the sequence. This is still true for GRUs and LSTMs, although they do have a bigger capacity to achieve longer term memory, therefore having a longer window to reference from. The attention mechanism, in theory, and given enough compute resources, have an infinite window to reference from, therefore being capable of using the entire context of the story while generating the text. This power was demonstrated in the paper Attention is All You Need, where the authors introduced a new novel neural network called the Transformers, which is an attention-based encoder-decoder type architecture. On a high level, the encoder maps an input sequence into an abstract continuous representation that holds all the learned information of that input. The decoder then takes that continuous representation and step by step generates a single output while also being fed the previous outputs. Let's walk through an example. The Attention is All You Need paper applied the transformer model on a neural machine translation problem. Our demonstration of the transformer model would be a conversational chatbot. The example would take in an input text, "Hi, how are you?" and generate the response, "I am fine." Let's break down the mechanics of the network step by step. The first step is feeding our input into a word embedding layer. A word embedding layer can be thought of as a lookup table to grab a learned vector representation of each word. Neural networks learn through numbers, so each word maps to a vector with continuous values to represent that word. Next step is to inject positional information into the embeddings. Because a transformer encoder has no recurrence like recurrent neural networks, we must add information about the positions into the input embeddings. This is done using positional encoding. The authors came up with a clever trick using sine and cosine functions. We won't go into the mathematical details of the positional encodings in this video, but here are the basics. For every odd time step, create a vector using the cosine function. For every even time step, create a vector using the sine function. Then add those vectors to their corresponding embedding vector. This successfully gives the network information on the positions of each vector. The sine and cosine functions were chosen in tandem because they have linear properties the model can easily learn to attend to. Now we have the encoder layer. The encoder layer's job is to map all input sequence into an abstract continuous representation that holds the learned information for that entire sequence. It contains two submodules, multi-headed attention followed by a fully connected network. There are also residual connections around each of the two submodules, followed by a layer normalization. To break this down, let's look at the multi-headed attention module. Multi-headed attention in the encoder applies a specific attention mechanism called self-attention. Self-attention allows the model to associate each individual word in the input to other words in the input. So in our example, it's possible that our model can learn to associate the word you with how and are. It's also possible that the model learns that words structured in this pattern are typically a question, so respond appropriately. To achieve self-attention, we feed the input into three distinct fully connected layers to create the query, key, and value vectors. What are these vectors exactly? I found a good explanation on Stack Exchange stating, the query, key, and value concept comes from the retrieval system. For example, when you type a query to search for some video on YouTube, the search engine will map your query against a set of keys, for example, video title, description, etc., associated with candidate videos in the database, then present you with the best match video. Let's see how this relates to self-attention. The queries and keys undergoes a dot product matrix multiplication to produce a score matrix. The score matrix determines how much focus should a word be put on other words. So each word will have a score that corresponds to other words in the time step. The higher the score, the more the focus. This is how queries are mapped to keys. Then the scores get scaled down by getting divided by the square root of the dimension of the queries and the keys. This is to allow for more stable gradients, as multiplying values can have exploding effects. Next, you take the softmax of the scaled score to get the attention weights, which gives you probability values between 0 and 1. By doing the softmax, the higher scores get heightened and the lower scores are depressed. This allows the model to be more confident on which words to attend to. Then you take the attention weights and multiply it by your value vector to get an output vector. The higher softmax scores will keep the value of the words the model learned is more important. The lower scores will drown out the irrelevant words. You feed the output vector into a linear layer to process. To make this a multi-headed attention computation, you need to split the query, key, and value into n vectors before applying self-attention. The split vectors then goes through the same self-attention process individually. Each self-attention process is called a head. Each head produces an output vector that gets concatenated into a single vector before going through the final linear layer. In theory, each head would learn something different, therefore giving the encoder model more representation power. Okay, so that's multi-headed attention. To sum it up, multi-headed attention is a module in a transformer network that computes the attention weights for the input and produces an output vector with encoded information on how each word should attend to all other words in the sequence. Next step, the multi-headed attention output vector is added to the original input. This is called a residual connection. The output of the residual connection goes through a layer normalization. The normalized residual output gets fed into a pointwise feed-forward network for further processing. The pointwise feed-forward network are a couple of linear layers with a ReLU activation in between. The output of that is again added to the input of the pointwise feed-forward network and further normalized. The residual connections helps the network train by allowing gradients to flow through the networks directly. The layer normalizations are used to stabilize the network, which results in substantially reducing the training time necessary, and the pointwise feed-forward layer are used to further process the attention output, potentially giving it a richer representation. And that wraps up the encoder layer. All of these operations is for the purpose of encoding the input to a continuous representation with attention information. This will help the decoder focus on the appropriate words in the input during the decoding process. You can stack the encoder n times to further encode the information, where each layer has the opportunity to learn different attention representations, therefore potentially boosting the predictive power of the transformer network. Now we move on to the decoder. The decoder's job is to generate text sequences. The decoder has similar sublayers as the encoder. It has two multi-headed attention layers, a pointwise feed-forward layer, with residual connections and layer normalization after each sublayer. These sublayers behave similarly to layers in the encoder, but each multi-headed attention layer has a different job. It's capped off with a linear layer that acts like a classifier and a softmax to get the word probabilities. The decoder is auto-regressive. It takes in the list of previous outputs as inputs, as well as the encoder outputs that contains the attention information from the input. The decoder stops decoding when it generates an end token as an output. Let's walk through the decoding steps. The input goes through an embedding layer and a positional encoding layer to get positional embeddings. The positional embeddings gets fed into the first multi-headed attention layer, which computes the attention score for the decoder's input. This multi-headed attention layer operates slightly different. Since the decoder is auto-regressive and generates the sequence word by word, you need to prevent it from conditioning to future tokens. For example, when computing attention scores on the word am, you should not have access to the word find, because that word is a future word that was generated after. The word am should only have access to itself and the words before it. This is true for all other words where they can only attend to previous words. We need a method to prevent computing attention scores for future words. This method is called masking. To prevent the decoder from looking at future tokens, you apply a look-ahead mask. The mask is added before calculating the softmax and after scaling the scores. Let's take a look at how this works. The mask is a matrix that's the same size as the attention scores filled with values of zeros and negative infinities. When you add the mask to the scaled attention scores, you get a matrix of scores with the top right triangle filled with negative infinities. The reason for this is once you take the softmax of the mask scores, the negative infinities get zeroed out, leaving a zero attention score for future tokens. As you can see, the attention scores for am have values for itself and all other words before it, but 0 for the word fine. This essentially tells the model to put no focus on those words. This masking is the only difference on how the attention scores are calculated in the first multi-headed attention layer. This layer still have multiple heads that the masks are being applied to before getting concatenated and fed through a linear layer for further processing. The output of the first multi-headed attention is a mask output vector with information on how the model should attend on the decoder's inputs. Now on to the second multi-headed attention layer. For this layer, the encoder's output are the queries and the keys, and the first multi-headed attention layer outputs are the values. This process matches the encoder's input to the decoder's input, allowing the decoder to decide which encoder input is relevant to put focus on. The output of the second multi-headed attention goes through a pointwise feed-forward layer for further processing. The output of the final pointwise feed-forward layer goes through a final linear layer that acts as a classifier. The classifier is as big as the number of classes you have. For example, if you have 10,000 classes for 10,000 words, the output of that classifier will be of size 10,000. The output of the classifier then gets fed into a softmax layer. The softmax layer produces probability scores between 0 and 1 for each class. We take the index of the highest probability score and that equals our predicted word. The decoder then takes the output and adds it to the list of decoder inputs and continue decoding again until the end token is predicted. For our case, the highest probability prediction is the final class which is assigned to the end token. This is how the decoder generates the output. The decoder can be stacked n layers high, each layer taking in inputs from the encoder and the layers before it. By stacking the layers, the model can learn to extract and focus on different combinations of attention from its attention heads, potentially boosting its predictive power. And that's it. That's the mechanics of the transformers. Transformers leverage the power of the attention mechanism to make better predictions. Recurrent neural networks try to achieve similar things, but because they suffer from short-term memory, transformers are usually better, especially if you want to encode or generate longer sequences. Because of the transformer architecture, the natural language processing industry can now achieve unprecedented results. If you found this helpful, hit that like and subscribe button. Also, let me know in the comments what you'd like to see next. And until next time, thanks for watching.